Right, so last time we stopped at, I'm gonna grade the quiz today and maybe post the grades. I'll try. So next week you guys will have the quiz grades. So last time we started to talk about the, do you guys remember last week?
Conjugate beam.
The conjugate beam, right? So for the conjugate beam, I started to make an introduction, but we didn't continue the topic. So we are gonna talk a little bit about what we talked last time. If you guys remember, if I have a beam like this, hinge and roller, and it has a load W, this beam, the shear force diagram, is going to be something here. This is Q, this is M. The Q for this beam is going to be something like this, positive and go negative, and both are equal. The moment is going to be all positive, something like this. That's all positive, and that's negative. If that's positive, that's negative. Do you guys remember what is the relationship between the load and the shear? If I want to get the shear from the load, what should I do? I integrate or I differentiate? Integrate. So the integration of negative W dx, and if I want to get the moment, I will integrate the shear Q dx. If I want to get the shear from the moment, so what I'm going to do? I differentiate the moment with respect to x. If I want to get the load from the shear, so it's going to be the differentiation of dq dx, and we proved this last time. This is the relationship between these three. So, as we know, the relationship between the deformation and the moment, we got it from the elastic curve differential equation. Do you guys remember the elastic curve differential equation? Do you guys remember? The d squared y dx squared is equal to moment over ei. Moment over ei. That is the relationship. And I told you this equation, you need to have it in your memory. And what is d squared y dx squared? Curvature. Exceed, right? So if I want to get the slope from the curvature, I integrate or I differentiate? Okay, so we have three quantities. We have y, and we have theta, and we have exceed. Theta is y, like when you differentiate y, right? Like, let's put dy dx. dy dx, and exceed is d theta dx or d squared y dx squared, right? So that's actually what, when we say deformation in a beam, we say these three quantities, y, theta, and exceed, because this is deformation, deflection, this is slope, and this is curvature, okay? So that's what the three quantities that we are interested in, and somehow these quantities are related. Like if you want theta, you differentiate y. If you want exceed, you differentiate theta. Same relationship between moment, shear, and load, right? So, like let's have the three beams here. Do the same. So the conjugate beam is using this relationship to find the deformation, the relationship between the load, moment, and shear, to find y, theta, and exceed. For example, if you know the moment all over the beam, you can divide the moment over ei to find exceed, right? So the easiest thing that I can find is exceed. It's very direct. You have the moment diagram, so basically this is m. Basically you divide m over ei, you can get the curvature at any location of the beam. That is the easiest quantity that I can get. So to get theta and y, it's a little bit more difficult. Why? So what you're gonna do, you are gonna take m and put it as a load on the beam, and then divide m over ei, and the load is gonna be, if it's positive, so you are gonna put it as a load going up, because that's the positive direction. And if I draw the shear force diagram of a beam that has a load m over ei, is gonna be something like this. something like this. That is the shear force diagram of this beam. But I know that the shear force diagram is the integration, if this is the load W, if I integrate this, the integration of W dx, that means like, if I integrate this, all right, if I integrate, because that is equal to d squared y dx squared, right? So if I integrate the d squared y dx squared is gonna give me dy dx, which is theta, right? So this is basically theta. So if you get the shear force diagram of this value, it's gonna give you theta. And the next thing, if you draw the bending moment diagram here, so it's gonna be something, for example, like this, and this is the moment, and that's also mean that is the integration of this, the integration of q with respect to x. And if I integrate q dx, so it is gonna be something, it's gonna be y, because when you integrate, that means, because this is equal to theta, right? And theta is equal to dy dx. So basically you are integrating dy dx, and this is means y. So I'm trying to tell you what all these means, but the summary is step by step. If I give you a problem like this, let me example. And in this example, I'm gonna put here roller, I'm gonna put here hinge, and I'm gonna put a load 30 kips. And the distances are 6 foot, and here's 6 foot, and this is 12 foot. And what I'm asking for, use the conjugate beam method to determine the maximum value of the deflection between support A and C. That's A, that is B, this is C, and that is D, all right? So, if I give you an example like this in the exam or in the homework, all what you have to do, draw the bending moment diagram, because I'm not interested into the shear. If you can't, what I'm interested in the moment, so because this is the only value that I use so that I can divide it over EI. I'm not interested into the shear. So draw the bending moment diagram, step number 1. Divide the bending moment diagram over EI and deal with it as a load. And draw the shear force diagram and the moment diagram for this load, then you solve the problem. That's it. If you got the shear, that means the shear is theta. If you got the moment, that means the moment is the deflection. And that's what I'm asking for. Determine the maximum value of the deflection. Okay? So if I'm asking only for the deflection, you can only get the moment. But if I'm asking for slope, you need to get both. Right? Okay, but before I solve this problem, I need to touch base on a few things that we need to do for conjugate beams. Conjugate beams need to be transformed to transform the original beam to a different end conditions. How? Like, for example, if I have a fixation like this, that's my original beam and it has any type of load. And what I'm asking you is to find the deflection here, okay? So, if, like, let's say it has this load. All right? So you will tell me, okay, so what I'm gonna do, I'm gonna draw the bending moment diagram for this beam, and it's gonna be something something like this, it's gonna be negative, and here's the moment, it's gonna be WL squared over 2, and there's the bending moment, and then you will tell me I'm gonna draw another beam, like this, and I'm gonna put this as a load on the beam, something like this, and this load is going down, something like this. I'm gonna tell you how to deal with this load, like, because it's a parabolic curve, it's not like something like this, but it's the parabola is going inside, not outside. I'm gonna tell you we're gonna make it a triangle minus a parabola, so I'm gonna tell you how to deal with it. But if I did it that way, and I got the bending moment and the shear force diagram for this, I will find a shear here, right? And I will find a moment here. Like once you draw the bending moment diagram for this thing, the thing is, you will find that the bending moment here is 0 for this conjugate beam, and the shear force diagram is 0 for this beam. And there is a moment and shear here. So if there is a moment and shear here, the moments mean theta, and the shear means deflection. So if there is a moment and shear here, that means there is a shear, and there is a moment, that means there is a theta, and there is a deflection. However, this beam has fixation here, and at the fixation, the shear, the slope is 0, and the deflection is 0. So this doesn't make sense, right? If I use the conjugate beam. So before you solve any conjugate beam problem, we do support transformation. We have to transform the supports to different supports that can give us right numbers. So let's see how we can transform these supports. All right, so for conjugate beam, there's a rule. It tells you if you have fixed free, any fixed support, like let's say here is the original beam. And this is the conjugate beam. All right, so if you have a fixed support, it's gonna be transformed into a free in the condition. And if you have it free, you transform it to fixed, right? Fix it, transform it to free, free, transform it to fixed. Why? Because at fixed, we know that the slope is 0 and the deflection is 0. And the only way to get moment and shear equal to 0 here is that to make this support free. However, here, there's a slope. Like if you draw the slope, there's a slope and there's a deflection at this point. Okay, here is the slope, theta, and there's a deflection, delta here. The only way to get a shear and moment at this support is to put fixation. If you put hinge, the hinge is gonna give you the slope, but it's not gonna give you deflection. The hinge is gonna give you shear, but it's not gonna give you moment. So the only way to get shear and moment is to put fixation here. And once I have shear and moment value, that means that I have theta and y. Okay? So fixation free, and free is fixed. All right, that's the very thing. If you have intermediate hinge in the middle, it needs to be transformed. Like if I have, for example, hinge. If you have a hinge at the ends, it's gonna be hinge. It's gonna be the same. Like if you have hinge, it's gonna be hinge. But if you have intermediate hinge at the middle, it transforms into a roller. And then this is gonna be hinge. So any intermediate hinge in the middle, why? All right, so if you have intermediate hinge in the middle, that means that intermediate hinge, it has rotation, like the slope is not 0 and the deflection is not 0. So you need something in the middle that can generate slope and generate deflection, that has moment and shear. And when you have a roller here, that means that if you have a shear, you are gonna have a shear here, or you are gonna have a moment here. Like either the moment is gonna be something like this, and definitely there's a shear. So we transformed this. What if I have a roller in the middle? Like what if it's the opposite? Like if I have hinge, and then I have roller in the middle. Okay, so if I have a roller in the middle, I need, like here, there's a slope, but the deflection is 0, right? Is there deflection at this roller? Like if this beam has loads like this and this, it's gonna be having a deflection, something like this, and then it goes to 0, something like this, and then it's gonna make something like that, right? That's how is the deflection at this beam look like. So the deflection is gonna be 0, but there's a slope because there's something here and there's a change of slope at this support. So what is the boundary condition that I should put in the conjugate beam? What does it mean if, okay, the slope is not equal to 0, but the deflection is equal to 0? Slope means, and the conjugate beam means shear, right? And deflection means moment. So what boundary condition that I should put here that can give me moment equal to 0 and the slope is not equal to 0? Intermediate hinge. If I put intermediate hinge here, it's gonna give me moment here equal to 0 if I draw the bending moment diagram. And there's still some slope. So if you should, like the summary, you should transform the boundary conditions. Fix it. It's gonna be free. Free is gonna be fixing. Okay? Any hinges or rollers at the ends is gonna stay hinges and rollers. We are not gonna change them. And if you have a roller in the middle, it's gonna be intermediate hinge. And if you have intermediate hinge, it's gonna be a roller. Okay? That is the 4 things that you should know. All right, so let's see how we can do this. Maybe we can try some stuff together. Like, let me put some examples to make sure that you guys understand it. Okay, so let's say I'm gonna draw the original beam here. Like if I have fixed, how the conjugate beam is gonna look like. What support I'm gonna put here? Hinge. How about here? Intermediate hinge. How about here? It's gonna be free. So you will tell me, but this, I can't solve it. It's gonna be unstable, right? If I put the load and I put everything, it's gonna be unstable. It doesn't matter. You are gonna make all this take the vertical reaction because this is not a real beam. So we are not talking about stability, okay? So you are gonna put everything and you don't care about the stability, okay? So, and then solve this beam, get the moment and get everything the way it is, and then you're gonna have the final answer. Why? Because this is not a real beam. This is a conjugate beam. It's just a manipulation to solve for the slope and deflection. But finally, the values that you get here is not a real moment and it's not a real shear, okay? It's just like a mathematical manipulation so that we can get the shear and the moment. However, this is the real beam. This is the one that needs to be stable and determinate so that we can solve it. Yeah, but then I'm not gonna give you one like this because this one is gonna be indeterminate from 3rd degree and it's not gonna take a lot of time to solve. I'm gonna give you something like this that is determinate and we can solve it, okay? But I'm just doing this as an example. All right, so let's, okay. If I have something like this, how the conjugate beam is gonna look like? What is the end support here? Free. Head here. Hinge or roller. Here. Hinge is gonna stay something like this. All right. And let's do something. Okay, this is interesting one. How about this one? Here and here, hinge or roller, and here, free. Okay. What if it's something? Hinge and another hinge. What I'm gonna put here? Hinge, stay the same, and then I'm gonna have intermediate hinge, and then I'm gonna have another hinge, and another hinge. That's how it is. Okay, let's solve this problem.
No question.
Hmm.
Why'd you say it's a hinge, for the second and the third one?
Which
Shouldn't
one?
it just be a roller?
You can do hinge or roller, because our problems doesn't have X components.
Okay.
Okay, that's
okay.
it, okay.
Thank you.
All right, so let's solve this problem. Okay, step by step, I'm gonna write right now what is the steps that you should do solving conjugate beams. Let me write them down. So you okay. So the steps to solve conjugate beams so that you don't forget. Number one, draw the bending moment diagram for the original beam. Number two, divide the bending moment diagram to homogeneous segments. Number three, calculate each area and divide it by EI. Number three, find the elastic load point of application. Find the point of application of each load. And also the direction, the point of application and direction. Okay, so let's find out about these three verbs. The first thing is to draw the bending moment diagram, and that sometimes gets tricky. Like sometimes if you have a concentrated load, let's say, draw some beams and having some examples. Alright, and sometimes you'll have like a bending moment diagram, something like this, that is very easy and it's a negative. Due to a concentrated load, it's gonna be something like this. Sometimes you have a concentrated moment and it's gonna give you a bending moment diagram negative, negative, or you are gonna have a distributed load and it's gonna give you a positive bending moment diagram. And sometimes your bending moment diagram is a trapezoid, something like this. Or it can be something like this, but there is a parabolic curve, something like this. How can I deal with these bending moment diagrams? The best way to do it, first, if it's a negative, is the load is going up or down if we put it on the beam? We get bending moment diagram so that we can put it as a load, right? And when we put it as a load, it's either a positive load going up or a negative load going down. If the bending moment is negative, that means that the load is going down. And if the load is going down, we need to find the point that the resultant. What is the resultant if you have a load in this direction and it's triangle and it's distributed? So I need to find what is the value here. If the value here is M and this length is L, so the resultant is at 1/3 from here and it's equal ML over 2, right? Okay, how about this? If this is M and this is M and they are equal and this is L, where is the resultant? It's here, right? And what is the value? ML. How about this one? It's gonna go up because it's positive. And parabolic curves that looks like this, the area is equal to 2/3. And if this value is M, this is gonna be M multiplied by L. Like imagine if you have a rectangle like this, and this value is M and this is L. This is the area is ML, but if this is a parabolic here, this area is 2/3 of the entire rectangle, okay? All right, this one, if this is M M1 and this is M2, the best way to solve this moment, we divide it into two pieces. Pieces rectangle and pieces triangle. The pieces rectangle, the resultant is here, and the pieces triangle is the resultant is here. And you guys tell me, if this is L, what is the value of the load here, the resultant? M1, L. How about this one?
M2 minus M1.
M2 minus M1
M1.
multiplied by L multiplied by, because that's a triangle, right? It's the area. It's gonna be 1/2. It's half. That's a triangle, right? Let's take this triangle out. This. What is the value of this? It's M2 minus M1, right? And this is L, right? The area of the triangle is half multiplied by L multiplied by M2 minus M1, right? Which is this height. That is the area, but if we want to find the distance from here to here is 1/3. Okay, how about this one? This one is we have to divide it into three pieces. Like I have to do this, and I have to do this. I have to find this, and this, and this. Okay, this one is this distance multiplied by this distance. The triangle is half multiplied by this distance and this distance. This one is 2/3 of this distance multiplied by this distance. Okay. All right. No, actually, if you are gonna, because there's two ways to find this. If this is like this, if you want to take this distance, you have to take this one, because that is the height and that is the length. But you can do it another way. You can take the horizontal projection, which is this one, multiplied by this one. Either it's gonna give you the same value. Okay, so just be careful when I'm gonna take you in a complicated stuff. Our problem is much easier than that, but you have to know these things. Okay. All right. So that's some basics. Once you figured out the moment, because that's the first step. We need the moment, so we do these 4 steps to get the moment. Once you know the moment, like let's say that our moment is something like this. What we did, next step, we put the moment over EI as a load on the conjugate beam, and then get the shear, and then get the moment, and your problem is solved. Okay? So first, draw the bending moment of the original beam. I'm gonna do this here. So this is the original beam. I'm not gonna change the support, I'm not gonna change anything. I have, here's roller, and here's hinge. But to draw the bending moment, I have to find the reactions, right? I'll not be able to draw bending moments without reactions. Okay, you guys tell me, without doing some Fy, some Fx, and moment, does any of you can guess what should be the reaction here and what should be the reaction here?
20 and 10. 20 and 10.
Where's the 20? Is the 20 here or here?
Yeah, right.
It's a close. Why? Because you have 30 and it's at 1/3 and 2/3. So this support is gonna take one of them, and this support is gonna take, like, you have to divide this into 1/3 and 2/3, and the 2/3 is close to the support that close to the load. The more the load close to the support, the more load that you have reaction here. So if this 30 came to C, C is gonna have 30 kips reaction. Once the 30 is going away, the reaction here is going less. So once you are done with the reactions, you will find that you have 20 kips here and 10 kips here. Okay, if you did some Fy's, 20 plus 10, it's gonna be 30. But in the exam, you have to do all the static equations, some Fy's, and you take the moments until you get the two reactions here. All right, we got the reactions. Right now, we can draw the bending moment diagram of the original beam. Okay, what is the moment here?
0.
0. And then what is the moment here? 120. Why? I multiplied 10 by 12 foot, so you're gonna have 120 kips feet. Okay? What is the moment here?
0.
0, because if you calculate the moment from the right, it's gonna give you 0. Okay, so that is the bending moment diagram. Is it positive or negative? It's a positive bending moment. Okay, so you have, this is positive bending moment. I draw the bending moment diagram, and it's two triangles. You are gonna have a triangle on the left and triangle on the right, okay? So I know where are the resultant. Like, to get the resultant of this triangle, try to deal with it as a two triangles. If you deal with it as a one triangle, it's gonna be a little bit difficult, okay? All right, okay, so I finished all these steps. I drew the bending moment diagram for the original beam. I divided it into two triangles. I calculated each area, very easy, I can do this. And I can get the point of application. The point of application is gonna be somewhere here and somewhere here, right? For the two loads. The second step is to get the conjugate beam. We didn't get to the conjugate beam yet. First, I have to draw the conjugate beam. If I have a roller here, in the conjugate beam, what is gonna be? It's gonna be roller, right? No, any hinge or roller at the far ends is gonna stay the same, okay? So this roller. How about the hinge, which is in the middle? It's gonna be intermediate hinge. Do you guys remember if I have a free end, what it's gonna be? It's gonna be fixed, right? Okay. Let's put the bending moment as a load on the new beam. So I'm gonna have this. Should I put M or M over EI? This is the conjugate beam. In the conjugate beam, we take the moment and divide it over EI, so it can be equivalent to d squared d squared y dx squared. And this is my new load, and it's positive. This is not a moment, this is a load. So I put like arrows, that means that the load is going up, something like this. All right? Okay, so that is my load. And here's there's zero because there is no bending moment here, so this is zero. Right now, this is the load on the conjugate beam. Is that determinate or indeterminate?
Determinate.
Determinate. Why? I have fixed here, and I have hinge here, so I have 4 unknowns, but this one is gonna give me another equation. So I have 4 equations and 4 unknowns. All right, so let's draw the shear force diagram, and let's draw the bending moment diagrams. Okay, so if I want to draw the bending moment and shear force diagram for this, by the way, the load is linear. What do you expect for the shear to be? It's gonna be first degree, second degree.
Second degree.
Why? Because this is first degree, so definitely the shear is a degree above this, so it's gonna be second, and this is gonna be third degree. So from my expectation, if I draw the bending moment diagram, here, what is the value of the moment? Sorry, well, I'm drawing the shear, sorry. What is the value of the shear?
Okay.
So I have to get some reactions, right? So to get some reactions, I have to divide this, the load, the same way that I did, and I need to get what is the value of the resultant here and what is the value of the resultant here. And by the way, this is very easy. How I know that this is 6 and this is 12. So if you want to know this, it's going to be 1/2 multiplied by 6 multiplied by the moment, which is here is 120 over EI. So this is 120 over EI. And this one is going to be 1/2 multiplied by 12 multiplied by 120 over EI. That's how I get the resultant. Then you solve for the reactions. It will be very easy for you to get the sum of the moment from this left, or get the sum of the moment about this. So once you solve for the reactions, you will find out that the reactions here is 480 over EI, and you will have a reaction here 600 over EI, and then you will have a moment here is over EI. Solving this problem, you are gonna solve it like any static problem, applying the 3 equations that you know, the sum Fy, sum Fx. Sum Fx is not needed because there is no x reactions. And take sum of the moment about any support. And the intermediate hinge, you can use it to take sum of the moment on the left or sum of the moment at the right, okay? So if you take summation Fy, you will find 480 and 600 is gonna give you 1080 over EI. And the summation of this load should be 1080 over EI once you finalize this. So you got reactions. Right now you can draw the shear force diagram. To draw the shear force diagram for this load, it's gonna be something like this. You're gonna go down 480 over EI, and this is gonna go up because you have a load is going up, it's taking you up, and it's second degree, so it's gonna be something like this until you come here. When you come here, you will find that the shear force diagram at this location is 680 over EI, and it's gonna be constant until you come here, and then it goes down the 600. Okay, I have two values at this location. I'm gonna double check this number. It's either 600 or 680 because it doesn't show clearly.
600.
600?
Yeah.
So both of them are 600s. Okay, so that's the shear force diagram. So it's gonna be something like this, this, and this. So this is negative, positive, positive. I draw the shear force diagram. The bending moment diagram, if you draw it for this one, the moment here is 0, and the moment here is 0. So you will find out that the moment shape is something like this. Okay? And then it goes up something like this. And the value here, you'll find it as 360 over 3600 over EI. Okay, that's the bending moment diagram. Right now, this is negative, and this is positive. So I have right now, how does the deflected shape look like for the original beam? Like, if you put a load here, definitely this beam is gonna bend like this, and if this is free, it's gonna go up. Like, if you look at the deflected shape of this one, so it's gonna be something like this. That is the deflected shape of this beam, which is similar to the bending moment diagram that we got for the conjugate beam. However, this is not what I asked in the problem. I didn't ask you to get me the deflection and the slope. I asked you to find the value determine the maximum value of the deflection, okay? This will take us to something about the basics. Oh, actually, all this, I'm not sure if the camera got it. All right, so maybe we talk here. Do you guys know how we can find the location of the maximum deflection? Like, let's say,
As a 0. C.
okay, so if you have a bending moment, like if I have a beam like this, if you draw the shear force diagram, it's gonna be something like this, and then it goes to the 0 and something like this. If you draw the bending moment diagram, it's something like this, right? So where's the maximum value of the bending moment diagram is here.
Where shear is 0.
And where is the shear is?
0.
0. And why is that? As you guys remember, do you remember the relationship between the moment and shear? Like, if you want to find the shear is going to be equal to dm dx, right? Okay. So if you know the function of the moment, like this is the moment, the bending moment diagram is function of x, right? Whatever, like let's say m is function of x. So if you want to find the maximum bending moment, if you guys remember from the differentiation, if you want to find the maximum of a function, you differentiate this function with respect to the change, so, and then equate it with 0. This is how to find the maximum, right? But we know that dm dx is equal to shear. So that means if you want to find the maximum moment, so find where's the shear is 0. And this is the same thing that we have here. Here, I know that the shear is 0, so definitely it's somewhere here. It's not in the middle, okay? Because the load here is not in the middle. Even if it's in the middle, it's still, because it's not a symmetric beam, okay? So we need to find out where the shear is 0. If we find out where the shear is 0, we can calculate the moment and get where is the deflection here, okay? So let me show you how to do this. Okay, for this one, do you guys have any strategy to find the point of zero shear? Okay, so let's think about it. So you have 30 kips here, and you have a reaction here. So if it's somewhere between these two supports, right? It's either here or it's either here, okay? But from my guess, I guess it's a somewhere here, because this is a big load, like 480, and I believe maybe this triangle is enough to be more like, okay, so you have 480 over EI, and this 480 keep getting less because there's load is going up, and then at some point here it stopped here at 0. So at somewhere in this triangle, this load was able to bring the shear value here to 0. So if I have this triangle is something like this, that is the 12 feet, and something like this, and I have the load is going up to the value of 120 over EI. Okay? All right. So if I said that the shear is 0 at a point X, like let's say this is the point X here, okay? And I said that I can assume at this point that's where the shear is 0. And I have a reaction here, I have a roller, and I have nothing here, and I have a reaction here going down, it's 480 over EI. Okay? All right, so I want to find what is the value of the load here. The value of the load here is 0. The value of the load here is 120 over EI. In the middle is going to be 60 over EI. But at distance X, what is the value of the load here? It's very easy. So we can say that this distance is 12 feet, right? So at distance 12 feet, the load was 120 over EI, right? So at distance X, what is the value of the load? The value of the load that we don't know is going to be equal to X over 12 multiplied by 120 over EI, because it's a linear relationship. If X equal 12, so it's going to be 12 over 12, 120 over EI. Okay? All right, so here I know that this is going to be equal to, it's going to be 10, so it's going to be 10X over EI, right? That is the value of the load. Okay, so if I get the area of this triangle, the area of this triangle is going to be, and the point of application is going to be somewhere here. Okay, so the resultant of this triangle is going to be X multiplied by 10X over EI multiplied by half. Okay, so it's going to be 1/2 multiplied by X multiplied by 10X over EI. That is the area of this triangle. And the shear is equal 0 when the area of this triangle, which is the resultant of this load, is equal to this reaction, right? Okay, so we can say that Q, the shear is equal to 0 at if the 480 over EI equal to half X multiplied by 10X over EI. Or the sum of the forces is equal to 0. This is going up, it's positive, and this is going down, it's a negative. So it's gonna have a positive value and negative value. I can't bring the negative value on the other side, so it's gonna be, but so it's the same thing. Like you can say like the sum Fy equal to 0. That's the way, the same if you wanna have the shears equal to 0. So you are saying that the up is the positive. So you are gonna have this as negative 480 over EI plus 1 over 2x multiplied by 10x over EI, and all this is equal to 0. Then you can bring this on the other side, it's gonna give you the same equation. So both are okay, all right? So what I wanna do, I wanna have the amount of load is equal to the amount of shear, this. So this is a second degree equation. You can solve this equation. You will find out after you solve this, you're gonna cross EI with EI, and you will find that x squared, here you're gonna have, actually, 1/2 multiplied by 10 is 5x squared, and this is equal 480. So you'll find that x squared is gonna be equal to this divided by 5, which is gonna be, how much, 96?
Oh.
Okay, 96, then you take the root, so this is gonna be 4.9 or something. No, 9.8. feet. Okay? So, if this is 9.8 feet, which means it's less than 12, that means our assumption is right. But what if you get the value of this 13 or 14? That means our assumption is not right, and we need to get the other triangle in the equation. Okay, that means that the point of the 0 is not in this triangle, it's in the other triangle. The value of this triangle is not enough to counter the shear coming from the reaction. And actually, I can know that before I solve the problem. How? Get the area of this triangle. This is 120 and this is 12. You multiply 120 over EI by 12 is gonna give you 144, 1440 over EI, which is bigger than 480 over EI. So this triangle generate loads more than the reaction here, okay? So that means that somewhere, piece of this triangle can be equal to this value. Maybe the piece that we got, like here, this piece. This piece is generating a reaction equal to this reaction. So I know right now where is the point of 0 shear. It's at it's 9.8 feet. So what I want to do, I want to get what is the value of this. So what I want to do, I'm going to take the moment at this location. Sum the moment, let's call this point is C. Sum of the moment at C, we need to find it out. Okay, the moment at C, which is at X equal to 9.8 feet. How can I get it? I have 4, and I'm going to say the positive is going this way. Okay, that's the positive moment. 480 is going down, that's the reaction, is going down, so it's gonna be 480 over EI, multiplied by the distance, and this is negative because it's going down, multiplied by the distance, 9.8 feet. And you have the positive moment is coming from the load, which is positive, and this is gonna be the area of this triangle. I have X right now is equal to 9.8 feet, so it's gonna be half, multiplied by 9.8, multiplied by 10x over EI, and I know X right now. So I have 1/2 multiplied by 9.8 multiplied by the load, which is 10 multiplied by X, which is 9.8 over EI. So once you find the moment, so it's gonna give you 3135.3 over EI, and that is the value of the moment here. And if I know the value of the moment here, so that is actually the maximum value of the deflection. So the value of the deflection here is 3135 over EI. You will find it's a little bit tricky, but if you system yourself step by step, first thing, draw the bending moment diagram, then put it as a load divided by EI on the conjugate beam, and then draw the shear force diagram and the bending moment diagram. And finding the point of 0 shear, which is the maximum moment, that's basics of structure analysis. Okay, so what we did here, you should have done it in the basic structure analysis class.
Question. That moment that you did for just from the shear diagram?
This one?
Yes, now.
Yeah, well, the moment that I got, I used the reactions and the loads to get the moment.
Okay.
So when I drive any moment, I always look at the original beam,
Original.
or which is the conjugate beam. Okay. All right. Even drawing the shear, I always look at this like the way that we have done this. I have to look at this load to draw the shear, and I have to look at this load to draw the moment. Same way here. W, I get shear. W, I get the moment. Do you guys have any questions? So any conjugate beam problem. Number 1, draw the bending moment diagram and then construct the conjugate beam, put the moment as a load on the conjugate beam, and then get the moment and the shear for the new beam that you have. That is the basics of the conjugate beam. All right, does any one of you have any questions? Is it difficult? It's a little bit tricky, but believe me, it's not difficult. What is difficult is the double integration method, because if you don't know, sometimes you get like difficult beams, and if you get integration that you are not used to or not familiar with, it's gonna be difficult. But this one, You get the moment and put the moment on a beam, and I'm gonna give you like a very simple problem that is determinant and is not tricky. You should be able to draw the bending moment diagram on any determinant beam. This is the basic structure analysis. And then if you put it on another conjugate beam that is determinant, also you should be able to draw the bending moment diagram. And also if I'm giving to you in the exam, the maximum that I can do, I have it to be linear because I'm not like trying to give you a problem that is like curved, and if you want to get, it's gonna be a little bit difficult if it's distributed load, okay? Because you guys are used to beams that has concentrated load or uniform load, but not used to a beam that has like a general shape or a function or like a parabolic load, okay? All right, so right now we finished the topic of deformation. So I'm gonna give an introduction about our next topic that we are gonna continue next week. And I uploaded actually homework 2, that it's on the deformation of beams and frames. So you will have questions about double integration method and also about conjugate beam method, just the 3 problems. And it's due next week, okay? All right. So the next topic that we need to talk about is the analysis of cables and arches. Let's start with the analysis of cables first. All right, so cables. So do you guys know when we use cables or you saw structures with cables? Where we usually find structures that has cables? Bridges, like if you have a suspended bridge or you have a stay cable bridge. Do you guys know the difference? Stay cable bridge, you have like a very huge column, like a tower, and the cables is coming from the tower towards the bridge. That is called stay cable bridge. Suspended bridge, if you have a cable that is something like this, and having a cables coming out of it to hold the bridge. So if you have something like this, and this is, for example, this is my bridge, and there's some cables coming from here. That is called suspended bridge, because it's suspended on this cable. If you have a column like this, and you have your bridge like this, and the cables is coming like this, that is called stay cabled bridge, okay? So all of these are cable structures, okay? What else? Sometimes in the stadiums, or in the big halls, and if you want to support something, you can have like when you want to cover the stadium, something like this, and the stadium is huge, and if you have a cantilever like this, it's not gonna work. So you make cables coming from this to hold the stadiums, whereas people sitting down here, right? Or big holes. So we use cables for like stadiums or holes that is huge, so that we can support cantilevers like this, okay? So sometimes there's no ways that I have to use cables. And cables, it's very efficient, okay? But what is the problem with cables? And also, yeah, there's one application on the use of cables that we see every day when we drive our cars. Like when the power network, right? If you always have like a transmission line, and the transmission line is a tower, and there's a cable that runs from this tower to this tower. You'll tell me, but this is not a structure, this is what? No, it's a structure. Structural engineers study how this cable perform against wind, against tornadoes, against earthquakes. I tell you what loads on this cable, it's own weight. The own weight of the cable is a load, right? So the problem with cables is that we need to deal with the large displacements, like because the cables doesn't have a stiffness. Okay, so once if the cables lost the anchorage on the left and right, it's gonna sag, and it's lose the like for example, if something happened here, this cable is gonna sag and then it's gonna lose its function. Okay, so that is one challenge about cables, and also the anchorage. You need to find a way to anchor this cable in something that doesn't allow large deformation. So that's the challenges that we deal with. Also, you need to put in your mind that cables is something, yeah, like something like this one. Cable can take tension, right? Can't take compression. So it's only tension. And you tell me, like if I have a cable like this, what is the bending moment that on the cable at any point? It's always allows rotation, right? So always the bending moment is 0. So it only have normal force. It can't take any bending moment because it doesn't have any stiffness. So any point on this cable can be dealt as an intermediate hinge. So if you cut at the cable and take the moment left, it's 0. The moment right should be 0 because it's a cable, right? It doesn't have any moment. There's rotation allowed here and there's rotation allowed here. It doesn't have any stiffness. So this is the most important information about the cables that makes them special structures. So let's use this information to put some basics on the board. So if I have a structure like, let's say, I have a support here, and I have a support here, and there is a cable in between these two supports. The cable is gonna be always look like this, like something like this, but I make it big. Like if you have a tower, like a power tower, something like this, and then you have another tower here, and there's a cable between these two towers. Sometimes you will feel that this cable is like straight line, but it's not. It is always, there is a sag on this cable. Why? Because it's like a big cable, and this cable is gonna sag something like this. So we call this the distance between the line between the two supports, and here is the sag. But this straight distance, we call it chord. So this is chord, and this is sag, and the sag is always vertical, measured from here to here. So this is sag. So you guys know what is chord and what is sag. Chord is the direct distance from the two supports, and the sag is the distance from the chord to the cable. All right, let's take a section in the cable. Like let's have a section here, maybe here and here, and take this piece out and do anatomy, like something. Let me put it here. The cable is going to be something like this. So once you cut in a cable, what forces you can find in this cable?
Only tension.
Only tension, right? And what is the direction? Is there a moment? Is there a shear? It can't take a shear. It doesn't. There is no cross section to take. There's a small cross section. Okay. All right. So let's put the forces. What is the direction of the tension that we were talking about? It is always in the direction of the cable, right? So if I cut the cable, so it's gonna be, the tension is gonna be this way, and the tension here is gonna be this way. So this is tension 2, and this is tension 1. It is always tangent to the cable. So if you want to find the tension here, it's going to be tangent to the cable. It will have a component horizontal, like let's say H1, and it will have a vertical component V1, and same thing here, H2 and V2. So that is the forces on the cable. Okay, so what is the loads that the most of the cables, what kind of loads they have? Most of the structures that has cables, it doesn't have load distributed on the cable, okay? But it has its own weight. And sometimes we find some cables that has loads, like sometimes Like, oh, I have a very good example for you. Do you guys see the traffic signals? Sometimes the traffic signals are posted on a pole, and sometimes it's on a wire. You have a cable, and then it comes out of the cable. That's an example of a cable that has concentrated loads. And sometimes you have cables that are for the power transmission, and it's only have its own weight. And then if we want to represent the own weight, it's going to be something like this. All right, let's say W, okay? All right, what we are interested in is the tension in the cable, and sometimes we need the angle theta, which is like if you wanna, the angle theta, which is the slope of the cable. It's something like this. If this is the tangent, and this is the horizontal, this is theta. If this is the tangent, and this is gonna be theta, and this is gonna be theta, okay? So this is theta 1, and this is theta 2, which is the angle with the horizontal. All right, so let's find out some stuff together. So let me look at this cable, like let me take this piece out. So I'm gonna have a support here, and my cable is running down something like this, okay? And let's make it like 2D. And my support is somewhere here. So if I want to look at this section, it should be stable. Like the tension here in this cable should be balance the forces and reactions here. So I should have a reaction something like this and a reaction something like this. Why? Because I know this T is gonna have a vertical component like this and a horizontal component like this. So definitely I need a vertical component up and a horizontal component the other way. So let's say that you have V and you have, let's name this one like T1, V1, H1, and let's call this V and H. Let's do something interesting. If I want to find the value of H, that's very easy. So I'm gonna do the sum of Fx is equal to 0, and this is the positive. So I'm gonna find out that H is equal to H1. There's no other forces. Why? Because I don't have any horizontal loads on the cable. All the loads are going down. So I only have this and this are equal to each other. Okay, so right now I want to tell you something. It says that if a cable only supports vertical loads and the horizontal component of the cable tension is always constant. What does that mean? So if a cable only have vertical loads, if you cut at any section and try to find the horizontal component is always equal to H. Unless is this cable have loads horizontal, like let's say have 10 ton this way. This rule is not right. It's not gonna be right. But if the cable only supports vertical load, the horizontal component at any cross section is gonna be equal to the reaction here, okay? So H1 is equal to H. If you cut here, it's gonna be also H2 is gonna be equal to H. If you cut here, H3 is gonna be equal to H. All right. What if I wanna find out the vertical component, or I wanna find the tension in this cable? How can I find it? If you know the angle here, theta, you can find the tension. Why? Because I know that T1 is equal to, let's say, H1. Both are right. If you want to find H1, the horizontal component is going to be equal to T1 cosine theta, right? T1 has a component horizontal and a component vertical. And if you know the theta was the horizontal, you can get the horizontal component of the tension, which is the horizontal, is equal to T1 cosine theta. If you want a V1, it's going to be equal to T1 sine theta, right? So if I know the horizontal, you can find the tension in the cable is equal to H1 cosine theta. And actually that is the general rule if you want to know the tension at any cross section in the cable. If you want to know the tension here, is going to be equal to the horizontal component here over cosine theta at any cross section. So any cable, if you want to find out at any cable, if you want to find what is the tension, and that's actually the important component that we are looking for. If you want to know the tension here, first you have to know what is the horizontal reaction here and what is the horizontal reaction here. Okay, that's the very thing I know. And how I know it, before I solve the problem, I find the reactions. Okay, that's the first thing. And then from the geometry, you find theta at any component. Like here, you try to find what is the value of theta here, what is the value of theta here. So if you know the value of theta, and you know the horizontal, basically you can say that t is equal to h over cosine theta. That's it. So that's all about cable. Next time, we're gonna practice how we can use these rules. So we learned the two rules today. For cables, if there is no horizontal loads, the horizontal component of the tension is always equal to the horizontal reaction at the support. That is number one. Number two, the tension at any cross section is equal to the horizontal component over cosine theta at this cross section. All right, so let me ask you something. So right now we'll learn this rule. T is equal to h over cosine theta. If theta is equal to 0, what is the value of cosine theta?
1.
It's gonna be 1, right? Okay. So 1, and what is the maximum value of cosine theta? Is 1, right? It can't be more than 1. Okay? So if theta is equal to 0, cosine theta is gonna be equal to 1, and the tension is gonna be equal to the horizontal. Now how this can happen, like if you have something like this cable is supported here and supported here, let's say hinge and roller, okay? It's gonna make curve like this. What is the theta here? Theta 0, right? So if you cut a cross section here, you will find that the tension is horizontal, and it's gonna be equal to the horizontal reaction here, right? That's right. But let me ask you, what is the maximum value of the tension? Where is it gonna be? Whereas the theta is much bigger. So it's gonna be here at the support. So here is the maximum tension is gonna be at the support. Why? Because that is where this theta is bigger. Once the theta is getting bigger, this number is getting smaller than 1. It's gonna be 1/2 or 1/3. So it's gonna be 1/2. So this horizontal is gonna be multiplied by 2. So it's gonna be much bigger. So here, I have two support. I have this support and I have this support. Tell me which one that has much more tension? This support or this support?
Top one.
Why? Because it's more theta. This one, it's almost horizontal. Okay? So this one has more tension. Next time we're gonna solve a problem like this and see which one has more tension numerically. Okay? Right, so that's it for now. If you have any question, try to email me. I send you the homework. Try to solve it, to practice, and see you guys next time.
Thank you.